Yeah, so today is a big day. It is the day where we finally get into supervised learning properly. And there's already a question that I will answer, which the question is, are the notes supposed to only be 2 pages that I posted? And the answer is yes. So like starting from today, a lot of the stuff I'll just write like live during the lectures, and then after the lecture, I'll share the corresponding file or PDF or whatever of the notes written out. Yeah, and the reason, like, okay, the other option is I could share the like live version that's like basically blank, have like maybe some plots or something, and I can also share the filled in version beforehand. But I'm almost sure that I'm going to fill it in slightly differently than the like prepared version of it. So I think it's better if I just share it at the end. Okay, so that's how things are going to go. So as I said, today is an exciting day. We're finally done with our math and probability review. And believe it or not, we're going to define what it means to learn well. And we're going to define kind of our learner. And we're almost going to be done the course today, except for, the next like 18 lectures of trying to like implement it and so on and make it an algorithm. But other than that, you kind of will know how like ChatGPT and stuff have been trained and so on after today. Here's my bold claim. Okay, so how is this going to work? And it's almost going to be a little bit funny how straightforward it maybe is. But let's start with the kind of elephant in the room, right? Which is so far, you have this data set, great. You got this learner, it's producing a function that predicts things, but we've never really, defined what it meant for a learner to produce a good predictor. Like suppose I had 2 learners and they produce 2 different predictors. Which one's better? Okay, so this is kind of the question we're going to try to answer. And then based on this answer we get, we're obviously going to design a learner that's going to achieve this objective as best as possible. Okay, so the question we really have is what is the objective of the learner? Right, we'll spend quite a lot of time answering this. And once we answer it, the algorithm will be almost obvious. And so the only thing that I have pre-written here is just kind of like reminding you of the setting and one little I guess notational thing that we're going to be using from now on kind of. So here's the setting, right? This is what we have. So our learner has access to a data set. And this is going to be important to highlight. They have, the learner, they have access to a data set, okay? That data set is a bunch of feature label pairs that are sampled from this distribution. And here's the very important part. This distribution is unknown to the learner, okay? He has data, or they, she, he, whatever. The learner has data, but it does not know what distribution it came from, okay? And that data, it also knows is going to be independent and identically distributed from some distribution, but it doesn't know what it's from. Okay. And from now on, yeah, these features, we're going to call them feature vectors, and the labels or targets, that's going to be the names. And the kind of assumption going on forwards is we're always going to encode this tuple as a vector, because we're going to want to do operations with it, like multiply it and matrix multiply, whatever, things like this, and add things and so on. So that's just going to be the assumption. And that really should not be, you don't really lose much generality, because if your values are just natural numbers, for instance, the number of rooms, you can always treat it as a vector, but it can only take numbers that are 1, 2, 3, 4, or whatever. So let's have some examples of what a supervised learning problem might be and how you encode the data, and then we'll get into the meat of it. So here's 3 classic sort of examples maybe. First one is that house price thing. So, your feature vector, maybe you have 3 features. So you just say you have a feature vector with 3 features. And then it's number of rooms, number of floors, and age of the house. And then this yi is going to come from just the real numbers, which is the price. Okay, and then in the wine case, we've seen this a bunch of times, but your feature vector is going to be 2-dimensional vector with an amount of chemical 1 and the amount of chemical 2. And then the label is just going to be whether it's 1 for a particular type of wine and 0 otherwise. Okay, here's maybe a more applicable one, and this is really kind of how it works when you're doing like image classification. And for instance, like in self-driving cars, they get an image, from the self-driving car, and they have to be like, oh, that's a stoplight, that's a pedestrian, I don't want to hit them, what do I see? So what really happens is like they get a pixel image, let's say like a 20 by 20 pixel image or whatever, resolution they use. It's probably better than 20 by 20, I hope. And then you need it as a vector. Like it turns out like most of the algorithms is going to be really nice to work as things as vectors. So we're going to encode it as like, just a giant vector. So take every single like row or every single column of this like matrix of the images and just encode it as a vector. So you get a 400 dimensional vector representing like the pixel value at every single one of those points. So now our feature is like this 400 dimensional vector. And you can just do the same things as we're going to be doing today. And so like maybe the label is like, here you're trying to classify whether it's a cat, dog, or bird. You could be classifying if it's like a stop sign, a pedestrian, a dog, whatever, a red light, a green light, and so on. Okay, so hopefully that frames how you're going to be encoding your problems. And so like, what is it? All I'm trying to say is that if I give you like a word problem of like, you have this problem and you have this information and so on, and you want to predict this stuff, you might be asked like, what would your dimension of your features be? What would be your labels and so on? And you have to like write this out, something like this. And that's important because in the real world, people tell you things in words and then you have to encode it into your mathematical objects, which we're going to learn how to manipulate here. Okay, and there's this other question, which is like, why are certain things features and why are certain things labels or targets? And that all comes down to basically what you care about predicting. So if you want to predict, and we've said this quite a few times, but like, if you want to predict the price, that should be your label. If you want to predict the type of wine, that should be your label. If instead you wanted to predict, let's say, the number of rooms, you should make that your label. And maybe the price, you have that available and you add that to your features. And so like, it's all about the end goal. Like at the end goal, you want this thing that's a function that's going to be able to predict like labels that you think are like hard or unknown for you to get. And the features should be kind of like the easy things for you to gather. Yeah. So that's about the like philosophical discussion of how you frame the problems. And now we talk about what it means to have a good learner. Okay. So yeah, here's our goal. We want to define an objective. And let us begin this journey by doing so in a kind of informal way, see what maybe are the issues with this, and then try to refine this throughout the lecture. Okay, so it's like, in words, it's probably something like, you want to define a learner. It's going to be this calligraphic A thing. It's going to take in a data set. It's going to output a predictor F hat. Okay, and here comes an assumption. Okay, kind of. Okay, so you want to do well on like a new feature, right? Or like roughly speaking, you're going to get like some new, let's say, feature that's not in your data set, and you're going to be tasked with predicting it correctly, kind of, right? So let me kind of write that. So like, such that for any kind of new, let's say, feature label pair coming from here, okay, and I'm going to put a point which is like, this is unknown to the predictor, but I'm just writing that it was sampled so that we can compare to it in a second. So like, you're just going to get this X as the predictor, or like this function. And the objective is going to probably be something like, I don't know, you want your predictor for this particular feature to output the correct label, which was Y. Okay, so this seems kind of innocent, and you might think we'd almost be done at this point. And we're going to see some slight issues with it, but before getting to that, let me just mention one kind of important assumption that has been made here, right? Which is that we care about doing well on features and labels that have been produced from the same distribution as where our data set came from. Okay, and so this can be framed kind of like two ways, which is like, this is an assumption that like what people say at test time or at inference time, or when you are using this predictor, like when you've You had this data set, you did your learning, whatever, you produced this F hat, and now you're like, okay, I'm going to use it in the real world, and I'm going to let it, whatever, predict house prices for me, and so on and so on. The question is like, what are these new houses you're getting? Are they really coming from the same distribution as where your data came from? And the assumption is that they are going to be, okay? So that you can frame it that way. Or you can be like, go the other way, being like, okay, I want to predict houses well, let's say in Edmonton. So what am I going to do? I'm going to gather data from the distribution I care about, right? If your end goal is to produce, like predict well from this distribution, maybe your data should be gathered from it. And so like, if you're framing it in the way that you're going to gather the data, you should probably gather data from the distribution that you're going to want to predict well on later on. Okay, and if these things don't match, then there's things called like, then it's called, there's a distribution shift. And then there's all sorts of things to do there and whatever, and we're not going to talk about it in this course. And so this is the standard assumption in supervised learning. Okay, so now let's have a look at what might be kind of going wrong with this type of objective. There's a lot of things that are actually sort of weird about this. And let's kind of just draw a picture to understand what's going on. And this will hopefully tell you a lot. Okay, so this x-axis is going to be like my x, and I'm just going to have a one-dimensional feature. And the y-axis is going to be the corresponding like label, let's say. And suppose the feature is like the number of rooms. And so there's, let's just say we're going to look at number of rooms being 1, 2, or 3. Right? Okay. And okay, so somehow we need to understand what would it mean to do well on like this new distribution stuff, right? So I want to somehow get a feel for like what is this distribution, and there's various ways we're going to do this. One way to think about it is like I can get an idea of what it looks like by just getting a bunch more samples from it, and then I'll get an idea of like roughly what what does it look like where are the samples more likely to appear, and so on and so on. So I'm going to do that. I'm going to draw like maybe, let's say you sampled from this like, I don't know, like 20 times or something, just to get a feel of what these X and Y's might look like in this particular example. So maybe for like the one-room house, you see something like this. You get like a data point here, another data point here, another one here. Maybe you get like this weird one here, and okay, that's enough. And then for like a two-room house, maybe you see this kind of pattern. And then the three-room houses, maybe you see like something like this. Some reason you have like a bunch of houses that have 3 rooms, so you have more data points there. It's like there's a bunch of points here. Like we're filling it. Maybe there's like 1 point down here. Okay. So this is just like to get a feel of what the distribution might be. And another way you can kind of like draw this is you can actually, if you remember, this thing can be broken kind of up to, you can break this guy roughly up into this like using this chain rule thing into a conditional times a marginal. And that can give you some information too. So you can write this as the distribution of y given x times the distribution of just x. And like based on the data we've seen here, you might, maybe the true distribution looks something like this. So like first let's draw what p of x might be. And so now I'm kind of like overlaying like extra data, but it seems like, an x value of 1, there's like 4 points here, there's 5 points for 2, and then maybe like there's like 10 points here. So maybe it's like you have something like this. So I'll draw like a little bar here. So maybe like this is the probability. It's going to be the PMF, right, of getting the value of 1. Well, maybe that's like 1/4. And then I'll draw another bar here. And just keep in mind, I'm overlaying a lot of information here. And maybe that's 1/4. So like once again, the axis for this is different than the axis for this. I'm just kind of giving you a feel of like what's the probability of getting. And then maybe this, based on the data we're seeing here, it's like the probability of getting, a house with 3 rooms is like 1/2. Which should make sense, right? It kind of looks like it's twice as likely to get a house with 3 rooms than there is a house with 1 or 2. Okay, so this just gives us a rough idea that maybe, if you gather houses in Edmonton and you just restrict yourself to 1, 2, or 3 room houses, maybe it's more likely to get houses with 3 rooms. Okay. And then the question might be like, well, what does this thing kind of look like? So this thing is like, if you restrict yourself to some amount of rooms, what is the distribution for the prices there? And maybe, you know, people like normal distributions, so maybe the distribution that the houses follow is like a normal distribution. And here I'm going to draw the PDF. And so like kind of like overlaying it, people will draw something like this. So maybe this is, maybe that's not perfect. I'll shift it down a little bit. And this is like kind of emphasizing that like the most of the mass is here, and so you're getting points kind of around here. And you can kind of imagine this, and maybe here it's like that. Okay, and this would be the PDF of y given x. For x equal to what? X equal to 1. This would be like P of y x equal to 2. And this guy's P of y x equal to 3. Okay, and now that we frame this, we're going to get a lot of insight, I hope, from this picture of what is happening. Okay, so let's start with kind of the first observation. Maybe, is there any questions about what in the world I just drew? Because if you don't understand this, there's going to be a lot of problems. Okay, great. So all we were trying to do is kind of just get a sense for what this distribution or what new data might look like. That's all I'm trying to frame. All right, so now let's look at our objective here, right? Which is, let's remind ourselves, so like we've got this predictor f hat. Let's remind ourselves, what is f hat? What kind of a function is f hat? Well, f hat, right? This guy is a function from, in this case, real numbers. Or let me make it just even a little bit more precise, just to kind of bring the point home. It's going to be a function from like 1, 2, or 3, right? Like, let's say that's the only numbers you're going to see, for instance, in terms of numbers of rooms. And that's going to map you to some real number describing the price, right? So let's remember how functions work. If you take in a point in the domain, like 1, you're only allowed to output one number, right? So that means that this function is going to, for the value of number of rooms 1, it's going to have to output one number. But you can see that, like, you know, I could get a house with one room that's totally different price than another house with one room. So there seems to be something a little bit funky going on with this already. And the funkiness is the fact that, like, well, you know, y can change for a particular x, because literally y has a distribution conditioned on x. And so somehow saying that, you know, our predictor should output the random variable y is very odd, because it has to output one number. And so we're going to have to try to address that. So the way we're going to address that is to like somehow measure how that number that it outputs like relates to what these y's or these like these labels are. Okay, so we're gonna roughly speaking, we're gonna want some way to measure how good is a particular value condition on x. So maybe you'd want to output something like this. Let's have an example of like f hat. So suppose f hat was like this purple function, and it like maybe outputted this, and maybe here, and maybe here. And intuitively, you might think that that's probably not bad, right? And why might you think something like that? It's probably something along the lines of, well, if I look at these values I've output, you know, it's not too bad. Like, it's pretty close to these points, and then like these points farther out, they're much less likely, and so I'm not as like worried about being so bad on those points or something like that. And same here, you're kind of close to the. Oh, okay. I think someone, I guess, joined the call in the class. Yeah, so maybe that, and so somehow you have like some notion of the fact that this point can be compared to other points. And so we're going to formalize that as like a function called a loss function. Okay, so that's going to tell you how like close your predicted value is really going to be to some other point, and we're going to want that to be kind of small. Okay, so we're going to have a new function called the loss function. We're going to use this like holographic L symbol, and that loss function is going to have to measure between 2 points, right? So that's going to be a function from, in this case, well, so in general, your labels come from a space y, so I'll write it this way. So it's going to come from y, Cartesian product with y. So it takes a pair of 2 labels, and it's going to output a value that is going to be non-zero, and it can be any real value that's non-zero, so the positive real number. And this is going to be a measurement of how much you're kind of away from this point, your loss relative to that point. Okay, so let me just tell you kind of like an example of what this function might look like. So it might take in like a y hat, That's your maybe prediction, let's say. And maybe to make this concrete, I'll just plug in f hat of a particular point x. Right, that's your predictor. It produces this thing. And then the second input will be the actual, like, a particular label. And I'll take the question in a second. And so, like, a natural way to maybe measure these two things, okay, is I want to take, like, f hat of x and subtract them. But there's, like, a slight issue, which is that, here, if you take f hat of x, maybe it's this, like, purple thing, and then you compare this point, sure, there's going to be, like, a positive kind of error or loss. But if you compare it to a bigger point, like this, then you're going to have a negative loss, and you probably don't want that. So you're going to want to somehow, make the negatives positives, and so you're going to take an absolute value. And this will be called the absolute value loss. Okay. We still haven't quite addressed the problem that, the y can take a bunch of values, and we're going to do that in a moment, but I'll take the question first.
You said the loss that it has to be not zero.
Oh, sorry. I should say it can be 0 or infinity. So 0 loss is like you're cooking. You got everything perfect. That would be the case. Like, when can that happen? Right? That can happen if you have a problem such that for any input x, there's always the exact same output. So that would mean something like, if I were to overlay like a third distribution, I guess, and I'll erase it to not make it confusing. The distribution would be what is called a Dirac distribution, where all the mass is at the particular point. And if it was like this for every x value, then you could really get a predictor that outputs exactly the right value all the time, and it would have 0 loss like everywhere. But of course, that's not going to be like the case in general, and so we're going to have some other numbers. Okay, so here we go. So now let's try to frame this kind of this problem. So this quantity here, if I like fix the x, then y can vary, and maybe a natural way to say like what you're going to care about, which y's you care about, are going to be based on like how likely you see them, right? So one way to like say this is you kind of want maybe, there's a bunch of y values that you could be getting, and to relate how far you are from them, you might want to do something like a weighted sum, right? Which is like how far are you from that, weighted by like how likely you're going to see that. And that's another way of remembering or thinking of what the expected value is, right? It's just a weighted sum where the weights are the probability of seeing the value, and you're multiplying those weights by the corresponding values. So for a particular like fixed x, you're going to want to minimize actually the expected loss. And I'll just plug in this loss here. So that's going to be, you're going to fix an x here, and you're going to compare it to the random y, and you're going to condition, and this is going to be kind of confused, this is conditioning. So it's going to be the expected value of this random quantity, conditioned on the fact that, I'll plug in x, that x is equal to, let's say, 1. So this would mean that I'm doing well when the number of houses is 1 here. So, okay. So now this gives us like a number to describe on average how close this like value, this purple thing is, relative to all of these random y's. So y here is the thing that's varying. We fixed x, and we're comparing it in this way of measuring. Okay. Let me just maybe finish the thing. So like I've only done this for the number of rooms being 1. But obviously I want to do that for like any possible input. So like you're going to want to do that in the case where it's 2 and 3. And that's the only cases we have, because I've simplified things to make it a little more clear about what's going to happen here. So you're going to want to minimize all 3 of these kind of things simultaneously. And this is like what is called a multi-objective problem. And okay, is there anything wrong with, like, do we run into any issues with this, right? So let's just understand what's going on here. I'm going to want to pick an f hat that now, based on how likely these points are, it's getting a point that's like close to the corresponding y's, but I'm going to want this to be good for every possible x value. And so you have multiple of these objectives to pick from. And you might, you're probably going to guess that this learner, the way it's going to, find an f hat is it's going to have to search across different functions, and it's going to need some way to compare them. So let's suppose there was 2 functions that it tried to compare, and we're going to see that there's going to be some issues in trying to compare them. So I'll give you one function, which is, let's say, here's a function for predicting house prices. So it predicts here terrible prediction, then it does well on these places. And then you have another guy, does well here as well, but predicts super poorly on this guy. So which one's better? Is I guess the question. And the answer is like, you can't really compare them because this red predictor here is doing better over here than the orange one, but it's doing worse over here. And so what people do in like optimization world and so on, when they have multiple objectives, is they take they do what is called, like they want to make it into one number, basically. And this process is called like scalarizing your multi-objective problem. And the way this is going to work is you're going to take all of your objectives and you're going to take a weighted sum of them. And you're going to weight them by whatever weighting you care about. Okay, so maybe some places you'll care more, so you're going to weight that kind of point more. Okay, so let's write that. That's what I want, or that's what we're gonna do, and that's called like scalarizing. So maybe I'll write it down here. Okay, so I've got this multi-objective problem. We're going to scalarize it now. And what is that going to look like in this example? Well, it's going to look like we're going to take the sum for x, where x can be 1, 2, or 3. That's 1, 2, or 3 rooms. And it's going to be the sum of this object here, right? Oh, that's not what I meant to do. Great. And the thing that's varying here is x. So we're going to put little x here, right? So now this is like, I sum up literally this, how well did my f hat do for a particular x, weighted by some amount. And what we have forgotten here is that I've forgotten to weight it, right? We need to weight it by a particular amount. And you're going to probably want this weighting, you're going to want it to sum up, well, just like x is coming from 1, 2, or 3, you're going to want it to sum up to 1. So that you, like, yeah, this should be kind of natural. So you're going to take this like weighted sum of this thing. Okay. Yeah, someone asked if this loss function is for k and n nearest neighbors. I don't think so. This is just like a supervised learning loss function rule. Yeah, that's the answer. Okay, so if you look at this object, you might notice that this just looks like an expected value again. Oh, yeah, okay, that might look like, yeah, it looks like an expected value again, because this thing sums up to 1. And the question is like, how do you pick your weighting? And the kind of a natural choice that people choose is that maybe we should weight it by just, how likely it is to get that number of rooms or that feature. And so this is where this part of the picture comes in. We've seen that, getting a room with 1, or getting a house with 1 room, maybe has like a 1/4 chance. Getting a house with 2 rooms has a 1/4 chance as well. But getting a house with 3 rooms, well, that's twice as likely as the other 2, so it's 1/2. And that's going to be the weighting we pick. Since it's more likely to get a house with 3 rooms, we're going to weight it by that corresponding like probability. And that should make some intuitive sense too. If you want to get this, like, we're kind of trying to get to, maybe I should say, we're trying to get to like some number here that's going to describe the quality of our predictor. And once we have that number, it's going to be kind of obvious. What is our learner going to do? It's going to try to optimize that number, or the function that gives you that number. So we're trying to get to that point, and we're basically there now. So we're going to remove this w, and we're going to put the marginal TMF of x. And that guy, of course, sums up to 1. All right. And yeah, this thing, as I said, is an expected value. And so let's write that out. And the way that's written is like this. And so you can actually wrap these expected values inside of each other. And sometimes people will emphasize like what distribution each expected value is over. And so maybe I'll put that in the subscript to make it very clear. So people will write like that this expected value is over the randomness in y. So it's over the distribution p of y given x. And here we have fixed, and we fix x, right? And the outer distribution is over the randomness in x. And so we write p of x. And in that case, so yeah, and then this x here, right? We had, since we were summing, we had this x as an actual value. when you write it as an expected value, you remove this part, and now you're summing over the randomness in X. This is how we used to write expected values. Okay, so hopefully this step makes sense. And now you might remember there was like a property from last class, but even if you don't remember the property, it should make like kind of intuitive sense what's going on, and we're going to write out the definition of things. So let's do it multiple ways, just for fun. So like there was a property last class that we said that the expected value of like some random variable z conditioned on x is equal to the expected value of z. And so in our case, this guy here, this is going to be z, and x is just going to be x. And so we're going to get that the thing above is equal to this, which is just equal to the expected value, and now this is over the randomness of x and y, of f of hat of x, y. Okay. And in general, this is going to be the expected value of your loss function with your predictor taking in a random feature. I should be writing x vector everywhere. Yeah, everywhere you see x's, they should be vectors. If I forgot about it, then it was an accident. And so your loss function of these two random quantities. Okay. And so let's just like, I'll write out this step a little bit more formally in a second, just to like maybe give you some more intuition. But this should start to like make complete sense. At the end of the day, like what's happening is you somehow, now we've got a number, right? This thing is just a number. And it tells us like how well does our predictor f hat do on predicting new labels. And it's kind of this like weighted sum based on the probabilities of getting the corresponding feature in labels. And notice that this all like checks out based on our probability knowledge, and hopefully here you're happy that you learned all this probability before. Now you understand that this is like what's going on here. This is your random variable x and your random variable y. And here I have a function f hat of a random variable x. Well, that's just a random variable still, right? So now this thing's a random variable and this thing's a random variable. And then we said, well, L is also just a function of these two random variables, which is totally fine, because now L of this thing is itself a random variable. And then we talked about taking expected values of functions of random variables. L, if you recall, maps to real numbers, right? This guy inside is an element of 0 to infinity. So we're all good. We can definitely take weighted sums of numbers between 0 to infinity. Okay. And so this object has a name, and this object is called your expected loss, unsurprisingly. I mean, like, I don't know what else you would call it, or it's the expected value of the loss. So they remove the of the and just call it expected loss. And kind of maybe a little bit more ancient is the word risk. And this is going to be important for the name of the kind of learner we choose. Okay, so what have we kind of concluded? It's something along the lines of that our learner should output a f hat that will minimize the risk, right? Okay. And maybe just for fun, what I wanted to do is just write out this thing to make it kind of clear to interpret how this is working with maybe some of your probability tools. So what I'm going to do is like, right, another way to like view this object is you can, like we already had equality everywhere. And so what we can do is we can actually just expand out this inner thing, whatever that definition is. And then we can see what kind of an object we get, and we can like think about that object as well. Okay, so what I mean by that is I'm going to take this thing, right? And I'm going to remove the expectation. I've fixed x here. Now this is my random quantity. I'm going to sum or integrate over it. And since y is continuous in this house labeling thing, I'm going to have to integrate over this function. So I'm going to integrate over, I guess like let's just do all the real numbers, but really the house prices are only going to be from 0 to infinity. And you're going to have to weight it by the corresponding conditional TDF of y given x with x equal to little x, or yeah. And that will take in as input the corresponding y, and we'll write it often like this. Okay, so this, I don't know, at this point you might think this didn't help you a whole lot. But let me just write one more step, which is like, if I put brackets around here, this is how you should think of it now. So the way we've kind of like made this objective into a single number now is as follows. We said, let's sum up over all possible feature values, which is 1, 2, or 3 here. Okay. And for every single one of those, let's just fix one of them. Let's hold them constant, right? That's what we're going to fix any one of these. And then inside here, x is now fixed. Oh, there's something we forgot, which is the integral notation of dy. That's the thing you're integrating over. So right, this is an integral over just y. And so, okay, so back to the intuition. You think about the sum, so let's fix, like we're summing over all the x's, let's fix a single x now. And so in here, x is fixed. And now what this is saying is that you would like your loss, right, to be small when it's weighted by the corresponding probability of getting that label when you fix that particular x. And then you're going to then weight that by the corresponding probability of getting every one of the x's afterwards. Okay, so that's good. So we've gone here, and then at this point, that's what our learner is going to minimize. And before telling you what the learner is, which is, going to be kind of obvious, I'm going to just give you some like notational information about how people break problems into what are called regression and classification problems. And then we'll come back to this. Yeah, and maybe, yeah, let's just do that. So at this point, this is going to be like our objective. And what we're going to do in a moment is we're going to come back to this objective, and we're going to kind of replace this with minimizing that expected loss. And then we're going to talk about how to do that. But before getting there, let me just tell you some notational remarks and so on, because these are, I guess, important names of things. So people call your problem a regression problem. Yeah, we call it a regression problem if your labels, so like each one of these y's that are an element of the label set, kind of like represent an object, represent something with order. And this is once again, not how you spell represent. This is once again just like a design kind of idea, like decision based on you. Like you look at your objects, it's like, okay, there are house prices. Is there any notion of one house price being closer to another? And the answer is like, yes, like, a $200,000 house is closer in price to a $201,000 house than a $1 million house. And that's all it really means. And so like, more or less, this is just like, going to just be some sort of like interval. Usually y, this calligraphic y set, is R or an interval. And so it'll be like some continuous thing that the values have some notion of being closer to one value than another. And so the examples for this, that's not the E I want, are something like, house prices. Prices are a classic, so there's stock prices. I don't know, weather prediction, like the temperature or something. There's a bunch of problems where, your prediction is like a real number. And, okay, and then for this, it turns out that this will kind of dictate the type of losses we're going to want to use. So we use the following losses. So we've already seen one of the loss functions, which is like this L of, yeah, I'll just keep the predictor in there. So L of, maybe not. So in general, this thing's like y hat is just like some predicted value. You compare it to another y, which is the label. And the first one we saw is this absolute value loss. And if someone says this to you, you should know what this is. For instance, in like an assignment, we might say like absolute value loss. Like, we expect you to remember what that means, okay? I think. Maybe we give it on the formula sheet, but, I think this is a reasonable thing to expect. And then why does this make sense? It's because, you're actually measuring the distances between labels. It makes sense to measure the distances in some way. And this object is like a metric, and it's we're not going to get into metric stuff, but it gives you a number for things that are closer or not. And another choice of this loss function that people will use, and we will actually use throughout, is the squared loss, and it's just the exact same thing as above, but things are squared. Okay. And I mean, this thing achieves the same goal as the above, which is that it makes your losses always non-negative, but it also squares them. And so squaring them maybe is a little bit weird. It will emphasize errors that are like far apart a lot more. So if you had like a, I don't know, a prediction that was, let's say, $100 apart from the correct value, it's now squared. So it's going to be like 10,000, right, of an error instead of an error of just 100. So it makes you really not want to screw up on far out outlier things. But the real kind of other issue, like reason we're going to do this is because at the end of the day, we're going to need to optimize. And if you remember how optimization kind of works, you're going to take derivatives. And taking a derivative of a squared function is a lot nicer because it looks like this than an absolute value function, which looks like that. And at least for the purpose of this course. But you can do it for the absolute value one. And then instead of taking gradients or derivatives, you have to do these things called subgradients. But we're not going to get into the details because the story is really the same. Okay, so these are the two losses you need to know about. And so when you have a problem with the squared loss, people will call this like, this is usually the regression problem, but you can also have a different. And the other is classification. And there we'll have a different loss because the labels don't have order. Oh, and maybe just one thing to mention, just for your knowledge of naming and stuff. I guess I didn't say this. So this guy here, right, this is called the loss. And sometimes people also call it the cost function or the error function. They're not different. They're just, people use different names, so I don't want you to, like, you know, when you go out into the wild to be confused by these names. And yeah, people use expected loss, risk, expected cost, expected error, these kind of things. In this class, we're always going to say expected loss and sometimes risk. Okay, classification. I guess the best way to do this is to just copy and paste this and add the word not. Or without. Okay, so I represent something without order. And so we've seen some examples of these kind of things. So like the type of wine. You know, if you labeled them by different types of wines, I don't really know my wines, but you can't really compare the words, you know, too easily. Maybe a better example is like type of image. So there's no real notion of like, you know, a cat is more similar to a bird than a dog is to a bird or something like this. Or at least we're not going to kind of assume anything like that. And I don't know, another classic thing is like type of disease. In like a medical setting, you want to predict what disease someone has. Okay. And so here we use, what did I write? What kind of losses do we use? Well, for this case, there's no way, we don't really want to compare things or being closer or farther. And so here we really are going to use a loss that's just like 1 or 0, depending on if you got it right or wrong. Okay, and so that loss function is the following. And it's usually written like this. So that's two cases. It's equal to the value 0 if y hat equals to y. So if you predicted correctly. And it's equal to 1 if y hat does not equal y. Okay. So that's your called the sometimes called the 0-1 or binary loss. 0-1 loss. Okay. So that's just these two settings. They have different kind of losses. Yeah. Maybe the demo. Yeah. So that's right. So like this second index, we're always going to think of as the actual kind of like value. Y hat is going to be the predicted value, and I'm just writing it in these like general, just using variables, so I don't have to keep writing f hat of x everywhere. But at the end of the day, we're always going to plug in f hat of x here. And so that's what this y hat is just kind of representing as a symbol. And yeah. in the question above?
Expanded classification. Can you assign scores? For example, can you just pick all partially right in say 2.5 specific 5?
I mean, you can pick any loss function you want, I guess, at the end of the day. You can like have a giant table of like, when you check these and these, people aren't doing that usually. And we'll actually see we're not even going to use this 0-1 loss for kind of the same reason as we don't use the absolute value loss, because it's going to be very hard to like take derivatives. So we're going to use some like smoothed version of this. We'll see. But yeah, that's all I have to say about that. And how this course is going to go is we're going to focus just on a regression for like a long time. And then we'll get to classification. And you can see that the story is like, once we understand how to do things for regression, we just change the loss to be the 0-1 loss. And then really a smooth version of it. And we'll see it's the same exact thing. So that'll be like one lecture of how obvious that is. All right, so now let's get back to formalizing this objective. So I'm going to copy and paste it. Oh, and change the things that need to be changed. Okay, so maybe I give it the objective is like more formal now, but not quite correct. Maybe I shouldn't tell you that. Okay, so yeah, so everything's fine. This is unknown to the learner. Maybe I keep it. Okay, I keep all these things, and then the thing we're going to change is this guy, such that, oh, you reckon I missed a very important sentence in this objective, which is our objective, right, is to define a learner such that for any new thing, this, oh, no, this is fine. Okay, this is fine. You want to predict that. But here I'm going to need to add a word after, which is such that for any new x and y, the expected loss, right, of f hat of x comma y is small. Or in other words, you want to minimize this thing. You know, output f hat that minimizes that. Okay. And you might think we're done, but is there any problem still about things going on here? Okay, no guesses. How about the fact that the data set is a random variable? Okay, so what's the problem here? So I guess I tell you. Here's the breaking news. So your data is random. Okay, so what that means is, like, roughly speaking, your data set could differ, right? I mean, you went and gathered, let's say you gathered 100 house prices. Well, those house prices could be different if you gathered them again, right? If you gathered another 100, and if you gathered another 100, and another 100, and these can change. And so isn't it kind of weird that, like, maybe you got lucky one time and the f hat you outputted based on that data was like really good, but then if the data set changes, you might output a completely like wrong f hat. So there seems to be like the same problem we've been experiencing before, which is that we're going to have like a multi-objective problem, which is we want to do well on every data set, right? And so, so yeah, we're going to address that in exactly the same way. Yeah, so D is random. That's that. And so this is the thing to keep in mind. If D changes, like if the value of D changes, right, which can change if you get a new data set, then your predictor f hat changes. And then if it did well for one data set, it might do worse for another. And then we have some problems because one learner might do well on some data sets in the sense that it might make this small, but then another learner might do well on other data sets, and we have some problems. And so we have another multi-objective problem. And in particular, you have like the objective. Oh, here's another important thing. So like we have this expected value, and it's really annoying to keep writing it around everywhere and so on. Like, I don't want to write this object. So we give it a name. And let me just do it above here. So back here, this whole thing, like the same object, it's going to be given the following label. So this is like a definition from the right side. The expected loss is given a capital L, and it's just going to take in the corresponding predictor f hat. and it's going to mean, right? It's going to mean what it means above. It's like you plug in f hat, you take the expected value and over these random variables. So everywhere I will be using an object like this, I can now replace it with L of f hat to make the notation a lot cleaner. So let's go back to the subjective and change this to be L of f hat. And maybe I just make it a little bit more clear. So f hat is A of D. And this is a random variable. And so this whole quantity is still random. Okay. So you have this multi-objective problem, which is like, here's one objective, is like, maybe, and so I'm going to write this calligraphic D for like an instance of the data set, kind of like little x is an instance of the random variable x. And here's your first kind of objective. You want to do well in, let's say, like some data set 1, which is a particular data set. And you also want to do well in like data set 2, and 3, and 4, and whatever. And there's a lot of data sets, potentially infinite. And just to be clear, each one of these DIs is an element of the usual place that the data sets are coming from, which is this set, right? The end data point data sets. Okay. So how are we going to address this? We're going to address it the same way as before, which is we're going to scalarize again. And what that means is we're going to care about the weighted sum of this thing, right? So yeah, I guess this is how you spell it. Okay, we're going to scalarize. What that means is we're going to care about the kind of like the weighted sum over these data sets. Your data set's probably going to be like a continuous random variable. And what is the set? Well, the set you're integrating over is x Cartesian product with y to the n. Now you have inside your random thing, which is L of your learner with the corresponding data set. Data set now is going to be fixed. So it's not random anymore when you plug it into the integral. And you're going to integrate over this times some weighting of that data set, D, and then this kind of ugly looking notation of DD. Okay, all I wrote is like a weighted sum basically, but as an integral because things are continuous. This is the scalarization thing, and you might notice that this looks like an expected value with this as the corresponding PDF. And then what is our choice going to be for this PDF here? Right? Well, the choice of that is going to be the corresponding PDF. And this is actually like, it's probably going to be some like mixed thing, you know, because like the labels are discrete maybe, and then the features are continuous. So like it's this complicated looking object. And this would be like the PDF or PMF or mixed thing for the corresponding data set. And we're never going to need to expand this out. Don't worry, really. Like this is just for understanding what's going on. So replace it with that. And then we get that this thing is equal to the expected value, where this expectation is over the data set now, of the expected loss of our learner that takes in the random data set. Okay. And this is so this is actually like the real kind of objective. Yeah, so let's just finish writing that out. So if we take this, we have the formal objective, and in a couple minutes we will kind of solve the problem too. Okay, so we needed to add the expected value out here, and now we have ourselves just a number. So this thing will give us just a number, which tells us kind of like on average how well is our learner going to do over all possible data sets. And yeah, and the way it means, like, what is, and then for a particular data set, what does it mean to do well? Well, it means to have small expected loss based on that predictor that you output for that particular data set. Okay. So this is like important to emphasize that like learner changes with data set, but when the data set is like fixed, then you're trying to minimize this expected loss. And so, yeah, we're going to talk about this whole like trading off between different data sets and so on a little bit later in the course. But for now, like at the end of the day, you have this data set. So like, what are you going to do with it and so on? Or how do we, like, how do we, I guess, achieve this goal? Like at the end of the, like, yeah, how do we achieve this goal? So let me write this a little more clearly. Like at the end of the day, you have this expectation over data sets, whatever, but your goal is to plug in an F hat here, right? That's what your learner is going to output to make this small, right? That's what your learner needs to do. It needs to output an F hat that makes this small, but it's going to probably use a data set and so on. But like, what's a naive way to like make this small? Like, how would you do this? Maybe you don't even need the data set. Like, and so the first idea that probably comes to mind, I guess for the sake of time, I just tell you, is like, yeah. So to make this small, yeah, like you just want to pick F hat, that minimizes this guy, right? That sounds kind of obvious. It's just like, this is just a number. F hat is just a function. You can search through all your functions. Let's forget about computational things we're going to get into in a moment, and then you can find the function that makes this the smallest and you're done, right? And so the answer is going to be, this would be great, but let's just remember, what does this guy look like? This L of F hat. Well, L of F hat is equal to like the expected value of the loss of F hat with X comma Y. And if you remember to calculate this expected value, it's gonna, when you expand it out, you're gonna need to know the corresponding PMF or PDF, which is you need to know basically the PMF or PDF or mixed thing of this guy, if you're gonna wanna calculate this value. So the story is, this is why I emphasized at the beginning, we don't have this. If we had this, you'd be done. Kind of. Well, to some extent. You could at least calculate this value. And then there's a whole question about how you're going to, search through all possible functions, which we're going to address in later classes. But in spirit, you'd be done. But we can't even do that because we have a problem, which is that we don't know this value. Okay. And now we're going to literally next, we're going to define the kind of learner that is going to be used everywhere in the class and was used to train ChatGPT and everything, is my bold claim. And what do you think you would do if you don't have this, but you have data? Is there any guesses? Okay. I guess I will break the news again, which is there's maybe like two options here. Well, probably you're going to want to use the data to like estimate something, right? And there's like two options. You can estimate this guy, like you can just estimate this, and then once you have an estimate, you plug it in, calculate this expected value, and then find the F hat that makes that estimate the smallest. We'll do that later, and that's like called learning kind of the distribution. But a more direct approach that is like often used is like, why don't I just, like if I want this expected value and this is a random variable, imagine this is like, let's just say this was like a coin flip. How would you estimate, or how would you like, estimate the value of a coin flip if you had like n coin flips? Well, you probably take the sample mean, or like you'd probably take, like, you just estimate the value of that coin flip. So you can just directly estimate this random variable. Okay, and here comes the definition of the learner now. Okay, so, okay, like, yeah, the learner A is going to be a function that we kind of call let me just write out the whole thing. The learner is going to be, so we wanted to minimize the risk, right? That was our goal. So the learner should really be called like the risk minimizer. But since we don't have the true risk, we have like the data dependent estimate of the risk, right? We're going to call this algorithm the empirical risk minimizer. Okay, and this has the name ERM. And okay, That was interesting. ERM, that's the algorithm. How does it work? Well, it's going to take in a data set, right? So, okay, maybe I write it like this. Like, its input, as we have seen, is the data set. What's it going to do with that data set? Well, it's going to do like two steps. There's going to be an estimation step, which is we need to estimate, the risk. So that's going to be estimating, getting the empirical risk. So it's going to look like this. And so far, we're kind of writing this in English. And the next classes are going to be about implementing this. So you're going to use D to estimate L of F, right? The expected loss or the true risk for all functions that are an element of the set of all functions, right? We've written this before. That are maps from X to Y. So, right, these are just the set of all predictors. And we're going to want to, estimate the expected loss for all possible functions. And then, obviously, after that, we're just going to pick the smallest one. And I'm just going to give this thing a name, this set, so we don't have to keep writing it, and we're going to have to change it in a moment. So I'm going to just call this set, the set of all functions, calligraphic F. Okay. And call the estimate a very natural name, which is L hat of F. So this is our estimate. And hopefully this estimate is close to this. This is our empirical risk. And now here's the minimization step, or what we call the optimization step. And maybe I should call it minimization, but I don't know. Okay. So there's optimization. And what's going to happen? Our learner is going to pick the F hat, which is an element of this calligraphic F that minimizes L hat of F. Hat. And that's it. It outputs the F hat. Okay. And now here comes some more fun. So, yeah, this is our learner. We're actually looking good here. You estimate, okay, there's some things to fill in. We're gonna fill this in, but you should imagine it's not gonna be maybe that bad. You're gonna get an estimate using data, right? Use your data set. We're gonna estimate L with L hat, and then you can imagine intuitively, if L hat is close to L for every single function, it's, I don't know, some tiny error in it, then it makes a lot of sense to just pick the best function based on L hat, based on the empirical risk. Okay, but there's two kind of issues that you might run into here, which is computational and statistical. And statistical means about how much data you need. And before you even get into computing things and whether you can search over all functions or so on and so on, you might ask okay, let's imagine I had infinite compute. How much data do I need? And the answer turns out that if you're searching over all functions, there is a very wonderful theorem name, and it tells you that there is absolutely no free lunch. And I'm very serious. This is if you ever take learning theory courses and machine learning, people are going to be yeah, there's just no free lunch theorem, and let's see what it tells us. And so, of course, I'm going to state it in this informal way, because we're not going to get into the details of it and everything, but the key is to understand what it's telling you. Super simple. So here's the story. Suppose you give me a learner. So if A, your learner, is ERM, right? And your ERM learner uses it. So okay, above we have this F, right? And you could maybe pick F to be smaller than all functions, right? But suppose that the ERM learner chooses F to be all of the functions, okay? Which we saw above. So if you pick F, and this is called your function class, to be all possible functions to look over, and you tell me that you're doing wonderful, And that means that, the expected value of the risk, right, which is this L, this expected loss thing, the risk of your learner for a, so this thing, remember, this is our final objective. You come to me, you tell me it's doing quite well. Like I can ensure that this is smaller than, let's say, like 1/4. And you can really put any constant in here that's like less than 1/2. Well, I'm going to tell you, and this is what the theorem tells you at least, that unfortunately, your data set must have been enormous. Then n, which is the size of the data set, right? How many data points you need? It's going to need to be as large as, okay, and let's before I write it, let's just reason about how this is going to go. So your function, kind of like, you're searching over all possible functions. And let's say the function is kind of going to be the one, like, let's do this easy case where, like, for every single feature, there's exactly one label that's correct, right? So now, there could be, like that, there could be some, like, so now there's a truly best function. And all that, like, you need to know that best function is the corresponding input-output mapping, right? Okay. So now let's suppose the domain is, like, finite, and this is going to be important for this. There's, like, an extension to the infinite domain, but let's suppose the domain is finite. And let's suppose there's, like, 100 possible values that the features could take, right? So now what happens? Like, if the functions are arbitrary, that means to learn the function or to get the best thing, you're going to basically need to know what is the corresponding correct label for every single input or possible to your function. So it's going to, like, basically what it's going to tell you is you're going to need to depend, the amount of data you're going to need is going to be literally the number of possible inputs to your function. And that can be, like, enormous in general, okay? And the way this is going to work is, like, it's not going to be that you're going to quite need this, it's going to be that you're going to need this over 2. And it's because, like, if you got this over 2, then you would have predicted correctly on half of all the possible inputs. But it could turn out that the best possible function on the other half is completely different from your function. So you could mess up, like, literally half of the inputs in this way. And so that's kind of the story. So, and X is usually, like, the domain is massive. And so this tells you nothing. It tells you the way you're going to learn here, if you want to search over all functions, is you're literally going to tell me, I need data that is, like, an example for every possible feature. And I'm just going to, like, memorize that. And that's it. Okay, so the resolution to this kind of situation is obviously that we're going to have to make f smaller. And this turns out to actually solve the problem. And so above here, all we do is we go into this ERM guy here, and we make a little bit of room for notation. And this equality guy over here is going to be changed with a subset, let's say strictly, okay, it could be equal, but if you're doing equal, then, good luck, as you saw from the no free lunch theorem. So we're going to have to make the function class smaller. And the smaller you make it, it's going to turn out the less data you need. Okay, and you might ask questions like, how do you pick this function class? Okay, so there's multiple things. So this guy is called the function class, set of functions you're searching over. It's just a set. It should be called like a function set, but they call it the function class. Sometimes people call it the hypothesis class, and they call these functions your hypotheses. Or sometimes people call it a model class. It's a set of models. And this thing, the choice of it, like the choice, reflects prior knowledge or your bias. And so in some way, it's going to reflect what you know about the problem is going to dictate the choice of this. So if for some reason you know that the data probably follows like a linear relationship, then you have no business considering quadratic and cubic functions here. Just pick lines, search over your lines, and you're good to go. So that's going to reflect this kind of prior knowledge. And okay, that's what I have to say about that. And then you just mentioned a couple things about how, so okay, how's the rest of the course going to go? The rest of the course is going to go about how do you estimate this, which is the next lecture. Who's going to talk about this, and then like, how good is this estimate, and how much data do you need for this estimate to be a good estimate of this? And then after that, so that's going to be addressing this. That's going to be like, how do we implement this with data? And then after that, we're going to talk about how do you actually search over all of your functions? Like, what does it mean to search over functions and minimize something? We've, in calculus, usually you're like, if you want to minimize something, you have like a number, and then you take a derivative of a function of a number. Now we're taking derivatives of functions. That's kind of weird. And it turns out that we're just going to completely avoid that problem by going back to good old calculus and numbers. And we'll see how that works. And just the other thing to mention is like, how does this work for like, let's say like ChatGPT and like these large language models? And so they really do this. They really like will formulate the problem, and it will be something like this. And you can like literally write this in a couple lines of code without like all the bells and whistles, which is they'll pick some loss function, like little l, so you have to pick little l. And since like, okay, how do you frame this whole language thing as like a supervised learning problem? You can frame it like, what are your features? Well, it can be any possible sentence. And what should be your prediction? Well, the prediction is going to be the next word, the correct next word. Okay, and like, yeah, so that's actually how they frame it. And so then what's the data? Like literally all the internet. And the way they do it is they'll take like just chunks of sentences on the internet and call like some chunk of this the feature, and then the next word, the correct next word, the label. And so you pick like a loss that's going to be like the smooth version of the 0-1 loss. You literally would like define this in your code. And then your goal is to then, okay, so you choose some estimate of this, and then based on that, you just run an optimization technique over your data set, and then you get out f hat, and f hat is like literally the model that you interact with. D is like an immense amount of data, which is like the whole internet. And now there's like libraries to do this in code, which literally will be something like you just define your loss function, you pick like your kind of like your estimate, and then you just pick like, you literally call like dot optimize, and then you get your output. And that's it, I think. That's all I have to say. So hopefully that gets you excited for figuring out how the rest of this stuff will work in the class. Okay.